All right, ready to dive into continuous machine learning, CML for short.
Let's do it.
So imagine if like your phone app, it always learns, always gets better, like it's got a mind of its own.
Yeah. That's pretty much the magic of CML.
But to get this, we need to shift gears a bit, away from how we usually think about software.
Right, like traditional software, you build it, you test it, you're done.
Yeah, ship it and forget it.
Exactly. But in machine learning, oh, it's a whole different ballgame.
Okay, so these models, they got to keep learning from all this new data coming in to stay relevant.
Absolutely. And that's where MLOps comes in machine learning operations.
MLOps, so it's like the crew making sure this whole learning thing actually happens.
You got it. Think of it as DevOps, but a whole lot more complex because we're dealing with models that are like constantly evolving.
Gotcha. So where do we even begin with all this? Like our listener wants to understand this whole continuous learning thing, right? Especially how the data changing affects the model and how to keep up with all the new trends.
Great question. So first, we got to understand the whole MLOps life cycle. It's like this loop, right, with three main phases. First, you got to design the whole thing, figure out the problem, see how machine learning can help.
So like, are we trying to predict customer churn or recommend products or maybe catch some fraudsters?
Exactly. Then you move into the experimentation phase, building and training the model. This is where data scientists really earn their keep, experimenting with algorithms, tuning the model.
And I'm guessing this is where the continuous part really kicks in. Like the model is always learning and changing.
You nailed it. And that brings us to continuous integration, delivery, and deployment, or CI/CD.
Oh yeah, CI/CD, I've heard of that.
It's like this automated process, right?
Yeah.
Testing, validating, and deploying new models as they're trained. Think of it like a pipeline. Every time the model learns something new from the data, it gets tested, and if it passes, boom, it's pushed out to the users.
Okay, that makes sense. It's all happening automatically.
Mm-hmm.
But what if the data the model was trained on, well, what if it's not relevant anymore? Like the world changes, but the model's stuck in the past.
That's the big challenge, data drift. Imagine you trained a model to predict, let's say, popular songs based on last year's trends. But then this year, boom, some whole new genre takes over. Your model's going to be way off, right?
Yeah, the data's drifted. It's not the same anymore.
Exactly. So the model's knowledge is outdated, doesn't match the real world anymore. And yeah, that can be a big problem, especially if you're making decisions based on those predictions.
Absolutely. And that's why managing data in CML is so important. But hey, it's not all bad news. There are some pretty cool ways to identify new trends as the data changes.
Okay, so we're not just sitting back watching the data drift by. We're actively looking for these new trends.
Exactly. We can use things like moving averages, smooth out the bumps, or time series decomposition to see those seasonal patterns.
So we're like data detectives, always on the lookout for clues to make our model better. That's a great way to put it. There are even clustering algorithms. They can help uncover those hidden patterns in the data.
This is all pretty fascinating. But how do we actually know when data drift is happening? Is there like an alarm that goes off?
Well, not an alarm exactly, but we have data drift measurement. It's all about using statistics to compare the data the model was trained on with the new stuff coming in.
Okay, so how do we measure this data drift? What are the techniques?
There are a bunch. You got your basic statistical tests like z-tests and t-tests. They tell you if the averages of two data sets are different.
Okay, I think I remember those from stats class a long time ago.
And then you got more advanced stuff like KL Divergence and Wasserstein distance. They measure the difference between the whole distributions of the data sets, not just the averages.
That sounds a bit complicated. Can you break it down a bit?
Sure. Imagine you're comparing the heights of students in two different schools. A t-test, it just tells you if the average height is different. But KL divergence, Wasserstein distance, they give you a more detailed picture of how the entire distribution of heights differs. Like, are there more tall students in one school, more short students in the other?
Okay, so it's about seeing the whole picture of how the data is changing, not just focusing on the averages.
Precisely. And using these measurements, we can decide if we need to retrain the model, adjust the algorithms, maybe even collect some more data.
Wow, this is getting complex. Keeping track of everything must be a real challenge.
It definitely can be. That's why understanding that traditional machine learning workflow is so important. Think of it like this. You start with your raw data, got to clean it up, prep it, like getting ingredients ready before you cook.
So chopping the data, getting rid of the bad bits, making it usable.
Exactly. Then you got to split this prepared data into three sets: training, validation, and test. Like studying for an exam. Training data, that's your textbook, your notes, learning the basics. Validation set, that's like your practice test, fine-tune your approach. And finally, the test set, the real deal. It shows how what you learned everything.
So we're testing if the model can use its knowledge on new data, right? Not just memorizing, but actually understanding stuff.
You got it. And this whole process, especially the training, it can really tax your computer. It's like a mental marathon for the machine.
Yeah.
But we got these things called continuous training accelerators. They're like specialized hardware, GPUs, IPUs, TPUs. They handle the heavy lifting, make it all faster.
Okay, so they give our computers a boost from machine learning. Makes sense, especially if we're constantly training and retraining models. We need all the speed we can get.
Absolutely. And once the models are trained, deployed, can't just forget about them. That's where continuous monitoring comes in. CM for short. Keeping an eye on your models, making sure they're behaving out there in the real world, making predictions.
So like a babysitter for our AI, making sure it doesn't make any big mistakes.
Exactly. We monitor things like model performance, is it still making good predictions? And of course, we're watching for data drift. CM helps us catch problems early, before they get out of hand.
It's like a well-coordinated dance, isn't it? Training, testing, deploying, monitoring, so many moving parts. How do we keep it all organized?
That's where the MLOps architecture comes in. It's like a blueprint for how everything works together. You need systems for your data, pipelines for automation, tools to monitor and manage your models. Luckily, we have frameworks like Vetiver. They provide a structure for building and managing these complex systems.
So these frameworks, they're like toolboxes for MLOps.
Exactly, giving us the right tools for the job. And one of the most important tools is version control. Remember how our models are always changing, being retrained? Version control systems like Git, they help us track all those changes. It's like a detailed lab notebook, recording every experiment, so you can always go back and see what you did, why you did it, and the results.
So it's all about traceability, being able to reproduce the process. We can see the whole history of the model, how it's evolved over time.
Precisely. That's super important for collaboration, debugging, even auditing. Imagine trying to fix a problem without knowing which version of the model was used, what data it was trained on. A nightmare.
Okay, so we've covered the whole life cycle. Designing, training, deploying, monitoring. We talked about data drift, continuous training, even those fancy accelerators. It's a lot to take in, but I'm starting to get how it all fits together. Anything else we should know about CML?
Actually, there is. Remember how our listener asked about keeping up with new trends and automating this whole process? Well, let's talk about AutoML, automated machine learning. Imagine building machine learning models as easy as dragging and dropping things on a screen. That's the idea behind AutoML.
Kind of like those website builders, where you don't need to know any code to make a website.
Exactly. AutoML wants to make machine learning available to everyone, even if you're not a tech expert. It handles things like data preprocessing, feature engineering, even picking the best model and tuning it, things that used to be really hard and manual.
Sounds like magic. But does that mean data scientists are out of a job?
Not at all. AutoML is a powerful tool, but it's not replacing humans. Think of it as helping data scientists, taking care of the boring stuff so they can focus on the more creative, strategic work.
So humans and AI working together.
Exactly. AutoML handles the routine, while data scientists bring their expertise, their creativity, their problem-solving skills. It's a collaboration.
That makes a lot of sense. Speaking of making things easier, what about these low-code and no-code platforms I've heard about? Are they related to AutoML?
Definitely. Low-code and no-code, they take this visual drag-and-drop approach even further. You can build applications with little to no coding at all.
So they're making it easier for anyone to build ML applications. Like, have you seen any interesting examples of these platforms in the real world?
Oh, absolutely. They're everywhere now. From marketing to finance, there's this no-code platform. It lets business analysts build predictive models without writing any code. They just drag and drop data, pick an algorithm, and boom, they've trained a model. It's giving people access to these tools who never had it before.
That's really cool. But what's the difference between low code and no code? Is it just how much coding you need to do?
Pretty much. Low-code platforms, they give you a bit more flexibility. You can add some custom code if you need to. No-code platforms, they're completely code-free, so easier to use, but maybe not as customizable. It depends on what you need and your technical skills.
So it's about choosing the right tool for the job.
Mm-hmm.
Sometimes you just need a simple screwdriver. Sometimes you need the whole power drill.
Great analogy. And as these tools keep getting better, they're making machine learning more accessible and impactful across all industries. It's an exciting time to be in this field.
It really feels like we're just scratching the surface here. There's so much more to explore.
There definitely is. But I think we've covered the key concepts, the continuous learning, the data drift challenge, the importance of monitoring, and all these amazing automation tools that are coming out.
And it all comes back to building systems that can adapt and learn just like we do.
Exactly. And as data keeps growing, getting more complex, continuous machine learning is going to be more and more crucial.
It's almost like we're teaching machines to think like us, to see those patterns and make predictions.
Well, maybe not exactly think like us, but to learn from data and adapt to change. That's the real power of CML.
So as we wrap up this deep dive, I want to leave our listener with something to think about.
I'm all ears.
If you could build a self-learning model, what problem would you tackle? What trends would you be most excited to uncover?
That's a great question to ponder. It really gets to the heart of CML, using technology to open up new possibilities, make the world a better place.
And who knows, maybe one day, thanks to continuous machine learning, those possibilities will become reality.
Yeah, and I think what's really exciting is it really feels like we're just scratching the surface. There's so much more to discover.
Right. Absolutely. So much potential, it's mind-blowing.
Right. Like, think about all the problems we could solve, the insights we could gain. It's incredible.
It really is. And I think that's what makes this whole field so fascinating. It's always evolving, always pushing the boundaries.
Exactly. And, as the technology matures, as we get better at managing data, at building these self-learning systems, the possibilities are just going to explode.
I can't wait to see what the future holds. But for now, I think we've covered a lot of ground in this deep dive. The continuous learning, the data drift challenges, the importance of monitoring, and all those amazing automation tools we talked about.
Yeah, we've packed a lot in. Hopefully our listener has a good grasp of the key concepts now.
I hope so too. And maybe, just maybe, this deep dive has sparked some new ideas. Got them thinking about how they can apply CML to their own work, their own lives.
That would be fantastic, because at the end of the day, that's what it's all about, right? Using this technology to make a real difference.
Absolutely. So to our listener out there, keep exploring, keep learning, and who knows, maybe you'll be the one to build the next groundbreaking CML application. Thanks for joining us on this deep dive. Until next time,